Now let's talk weather radar, right? So we can access weather radar from the FAA at aviationweather.gov, Aviation Weather Center's website. We can go down to observations and click on radar, and it's going to bring us to this screen here, radar imagery. And then below that, you have a few more options, right? We could go ahead and click on a region like the Tampa Bay region and look at a nice composite image compiled together. Or we could go ahead and look at just a single site radar for the Tampa Bay area. So we can look at that. Now, how radar works is we have all these stations put together and they build a nice composite image for us that we're used to seeing. We're used to looking at radar and just seeing these huge storms moving across the United States. Well, those storms are not all detected just by one radar station. They're built together. This is a composite image of many radar stations all put together, and the more radar stations you have nearby, the more accurate it's going to be. And we're going to talk about the limitations and the hazards associated with weather radar here in a moment. But let's go ahead and look at the National Weather Service's station chart that shows us all of the stations around the country. Now in the lower 48, we have all these stations depicted here, and it shows the coverage they tend to get, all right? So the shading is based on how much they can see with 4,000 feet above the ground, 6,000 feet above the ground, they can see a little bit further out, of course, and 10,000 feet above the ground, they can see even further out because there's less ground clutter, less trees, less buildings in the way of these stations. These stations have some serious limitations, though. They really can't see above them, and they take a while to make a nice composite image. So how it kind of works is they scan in layers, and they look at a certain tilt angle or a certain angle, and they scan the sky in this narrow layer, and then they tilt up a little bit, and they scan again, and tilt up a little bit, and scan again, and keep doing this, and form a nice composite image. And then all of those stations work together, and the computers compile all of that data to make the nice composite image we see that covers the entire United States, because there's obviously not a single radar product out there, or radar sensor out there that could possibly see the entire United States, because guess what? The world's not flat, it's curved, so those radar beams travel in a straight line. That's why you need stations all over the place. You can't just have one that does it all. Now, it's kind of important to know where all these stations are because that tells you how accurate the radar is going to be when you're looking at it, all right? So there's a cone of silence directly above these stations, and they obviously can't see below the treetops and below buildings. They can't see through anything solid. They're just looking line of sight and then getting a bounce back, a radar return off of moisture, liquid falling from the sky, rain. So they can't see clouds. They can only see it when the rain begins. They can only see storms once it starts raining. So once it's already past that cumulus stage and mature stage and it's getting into the dissipating stage where it starts to rain itself out, then it's going to show up on radar. And the more of these stations are closer together, the better picture you're going to get. If you're in an area where they're spread pretty far out, you're not going to get a very accurate image. And that's just one of the many limitations associated with this. Let's look at some other limitations here, like ground clutter is a big one. So we can see this image here around Tampa. There's a lot of ground clutter around it. It looks like there's radar returns near the station. That's just ground clutter. And further out from the station, you're not going to have that because the way the station's looking up, it's angled out. It's not going to detect trees and buildings and things like that further away from it. So within 10 nautical miles, you have to kind of worry about ground clutter. You have to worry about things like wind turbines. They can generate some really weird radar returns when there's really little or no precipitation and make it look like there's a storm out there. You also have to be aware of beam blockage. So if there's a tall building or a tall cell phone tower or something very big near the radar site, it's going to create this huge gap in what it can see unless there's another radar station very close by to it that can then fill in that gap coming from a different angle. But if there's a big tall building, you're going to get beam blockage. These little narrow gaps where it appears there's no weather, there's a little path for you to fly through, but there's not. There's definitely weather there. And the only way you're going to see it is if you have a good, accurate composite image from multiple stations. Some of the other problems we get with radar are ghosts and angels. Now, not the kind you know from the movies, but a radar ghost is pretty common in the warm season, in the warm summer, right towards sunset, when you get super refraction from all that haze in the air, and you'll get radar echoes around 15 decibels. And decibels are really important to us because we know radar is green and yellow and red and purple, and those colors mean something to us, right? When it's yellow and red and purple, it's really bad. We need to stay away. But those are just corresponding to a certain decibel level. In any of these other providers, there's so many other providers and apps you can download that are great, but they can all assign their own arbitrary color scale to the decibel level. Decibel level is the one constant throughout all of the providers. If you actually look at what the decibel is, that tells you how intense the rain is, right? So when you're getting really intense rain, it's always going to be a certain decibel level, but it could vary in color depending on whose charts you're looking at. Now, angels will appear typically only in clear air, just like ghosts, and they're going to be caused by things like bats or insects or something, typically in the evening when they're caused by bats departing from caves, or maybe early in the morning when birds are starting to fly around, take flight for the day. Typically only happens in very clear air because any sort of moisture in the air is going to block those very weak returns. Angels and ghosts are all fairly weak returns, and they typically don't have a ton of movement associated with them. And that's how you can really tell it apart from actual rain, because typically regular rain and thunderstorms actually move at a nice, slow, even pace, relatively speaking. Some of the other limitations with radar are not picking up things like stratiform clouds that are producing rain. So very low-level drizzly precipitation may not be depicted because it can't see that low due to ground clutter and due to obstacles blocking the radar sight. So you may not actually be able to see low enough to pick up that very low, light, drizzly precipitation. Luckily for us, that very light drizzly precipitation is not nearly as dangerous as big thunderstorms. And of course, the taller the precipitation is, the more it's going to be picked up on radar and the more hazard it is to us, because if all that water went up, then obviously there's a lot of energy that lifted it up and a lot of energy that's going to fall down right back on top of our heads as we fly near it. Now, the last thing I'll leave you with before we look at a real-world application of using radar both from the National Weather Service, radar on an actual aircraft equipped with onboard weather radar, and then actually just looking out the window and seeing what we see, compiling all that together, before we look at that real-world case study, the last thing I want to leave you with, very important, especially for a lot of us that are flying with ADS-B and getting weather piped into our cockpits, is that weather is old, and oftentimes it is older than the timestamp on it. So each weather radar station out there in the United States, every single one of them, is going to make about 5 to 14 separate elevation tilts as it scans the sky. It's going to take about 4 to 11 minutes just to generate that initial image. Then it's going to take some length of time greater than that to actually form that composite or radar mosaic image with all those other radar sites and then feed it into us. The timestamp that's often assigned to these, the valid time of the observation, is the time assigned to the product, which is at the end of the last radar scan. So the first radar scan began 11 minutes ago, and then the time they stamp on it is when the last one is made, but a lot of stuff changes in 11 minutes. We can look at this little video here. This is a time lapse of thunderstorms building and raining themselves out, and guess what? This is 8 minutes long. This is what can occur that quickly in Florida or Texas or anywhere there's thunderstorms. They can change very rapidly, move very rapidly, and change intensity very rapidly. So be very aware of any weather that's being piped in, whether it's on the internet, on your cell phone, on aviationweather.gov. All of that stuff is old and out of date if you're looking at it on any sort of device besides looking at real onboard weather radar on an aircraft. And onboard weather radar on aircraft range into the hundred thousands of dollars, if not millions of dollars on many of those bigger jets. Very expensive, very useful. That's how the airliners keep us safe when we're flying on the airlines. They can avoid weather very well. We simply do not have many of those tools available to us in GA, and it can be very misleading to think that you do on your cell phone or on your iPad or in with ADS-B. That stuff is old, and things change very quickly out there. So if you see weather and you're trying to avoid it, give yourself a huge, wide berth away from that weather as you're flying around it on your radar screen in your cockpit if you're getting ADS-B weather in, because it could very have easily moved greatly since that last image was taken, and then it finally made its way piped into your cockpit. So now let's go ahead and look at a case study of this corporate jet coming in at about 10,000 feet. We can see the weather above the airport moving in from the east. They fly around it as they come in, they land, and then they're stuck out on the ramp. Nobody's out there to help them because of lightning, and so they get to watch the weather roll in over top of the airport, both outside the window, looking at the composite image on the cell phone and iPad, and then also looking at the onboard weather radar on the actual aircraft.